Thank you, everyone, for coming today to talk. Like, I know it has been like a really long week of talks and like meetings and like talking about research. So I truly appreciate that you are taking an hour of your time to come see me talk about maintaining plasticity independent of architecture through selective reinitialization. Like Rich said, this is work that is an extension of our work done in the Nature paper. And there are two main concepts in this title that I really want to emphasize. The first one is maintaining plasticity, or conversely, preventing loss of plasticity. The second one is selective reinitialization. So loss of plasticity is the problem that I'm going to be focusing on, and selective reinitialization is the solution that I propose for addressing this problem. So I really want to take some time to help you understand these two concepts. Um, so what is loss of plasticity? Okay, sorry. Okay, so what is loss of plasticity? I like to explain loss of plasticity with an example. Let's pretend that we have a neural network that is being trained to classify digits from the MNIST data set. So the network observes one of these images, and it has to return a label corresponding to from 0 to 9. And let's pretend that we train this network for some amount of time, and we keep track of the online accuracy as it's learning. And then we decide to plot that. And I'm plotting the average online accuracy of this network. And let's say that I train it for some time, and when I plot it, I get an accuracy that looks like this, maybe about 10%. Now, this is just a hypothetical scenario, so let's just assume that this is the accuracy that the network gets in this problem. Now let's pretend that I scramble the pixels in images to create a new data set. Why am I doing this? It doesn't matter. Pretend that this is something that I want to do. The main thing is that I apply a permutation to all the pixels in the images, same permutation, so that it changes the images, but it still preserves the mapping from images to labels. So now I take the network that I had already trained, and I continue training it in this new data set. So it has to relearn the mapping from images to labels. And my hope would be that when I train this network, when I continue training it, I would observe maybe an increase in performance. Let's assume that that is possible. This is a hypothetical scenario. I would like it to at least improve a little bit. And then let's pretend that I apply a new permutation and I keep training my network. And then I will maybe a tiny improvement. And then if I keep doing this over and over and over again, I would observe something like this. At some point, the network would plateau at some level. That is the ideal scenario, where like the network first has shown some performance, maybe some improvement, and then it plateaus. If I cannot get that, it's an ideal scenario. So if I cannot get that, I would at least settle for this. A network that keeps learning and achieves the same level of performance throughout all the permutations, which is not very unrealistic because all these problems are equally difficult. However, if we actually run this experiment with a neural network, what we observe is something like this, where the network does improve performance after a few permutations, but after a while, it starts losing performance. And the problem is actually much more severe because if we increase the number of permutations, we observe something like this, where initially it achieves a really good performance after a few permutations, but at the end, it loses about 10% accuracy compared to the beginning. And this is exactly the problem of loss of plasticity, the loss of the ability to learn in neural networks. Everyone is still with me? Okay, cool. So the problem that I'm tackling and the solution that I propose is selective reinitialization. And selective reinitialization is a very simple idea. It's just selecting parts of the network to be reinitialized every so often in order to maintain plasticity. Even though this idea is simple, there's a lot of nuance in how it can be implemented. For example, let's assume I have a neural network with some input units, some hidden layers, and some output units. The first thing I could do is reinitialize the whole network. So here in green, I'm just presenting all the new weights that have just been reinitialized. So that's one way to selectively reinitialize the whole network. Another thing that you could do is maybe choose a layer in the network, such as the output layer in this case, and reinitialize that layer. Another thing that we could do is choose a hidden unit in the network, or maybe several hidden units, and reinitialize all the weights that are connected to that network. And lastly, we could also select a set of weights in the network throughout the whole network, and then reinitialize those specific weights. They are not attached to any specific hidden unit or any specific layer. They are just dispersed throughout the whole network. So there are 4 ideas: reinitialize an entire network, reinitialize a layer, reinitialize hidden features, which is also an algorithm called continual backpropagation, which is the one that we introduced in the paper that Rich was mentioning before. And finally, reinitialize weights. All these 3 options have been explored, but nobody has really tested reinitializing weights for maintaining plasticity. And that's exactly what I'm going to be doing in this talk. Introduce an algorithm called selective weight reinitialization and compare the performance between selective weight reinitialization, that means reinitializing weights, against continual backprop, which is initializing features. Okay, and I'm just going to jump straight away to the main takeaway of the talk. And that is that selectively reinitializing weights is more flexible and more effective at maintaining plasticity than selectively reinitializing features. Now, this is still a little bit vague, so I'm going to give you more details throughout the talk. But if you want to zone out for the next hour, this is the only thing that you need to remember. All right, so the next of the talk is going to go like this. First, I'm going to talk about continual backprop and how it succeeds and sometimes fails at maintaining plasticity in the permuted MNIST dataset that I showed you at the beginning. Then I'm going to talk about selective weight reinitialization in permuted MNIST. I'm going to give you the definition of the algorithm and show you its performance. Then I'm going to compare the 2 of them, reinitializing features against reinitializing weights. And finally, I'm going to show you examples of loss of plasticity in modern architectures and how reinitializing features and weights maintain plasticity there. And then I'm going to finish with some concluding thoughts. All right, so I'm going to just start with section 1, continual backpropagation. And I'm going to start by giving you a description of how the algorithm works. Let's pretend we have some hidden layer anywhere in the network. What continual backprop does is, first, it measures the utility of each feature in the hidden layers. So we have a utility function that gives us a number for each of these and tells us how useful that feature is for the network. Then we select a feature in this hidden layer or a number of features. We select the ones with the lowest utility. Then we reinitialize the input and output weights of this feature. For the input weights, we just use the initialization distribution. And for the output weights, we just set them to 0. And finally, we protect this feature for some number of updates so that it can no longer be reinitialized through this same process. So there are 3 different choices in this algorithm. First, there's the replacement rate, how many features and how often to reinitialize features. There's a maturity threshold, which means how long to protect a feature from being reinitialized. And then there's a utility function, which tells us how useful they are, so that we can rank them and then reinitialize the ones with the lowest utility. Any questions about how this works? Okay, so I'm going to move on. Let's look at the permuted MNIST problem. First, I'm going to give you some details about the problem. Like I said, the network is just trained on permutations of the digits in the MNIST data set. I'm going to train for 1,000 permutations. Each image in the data set is observed only once. After we just apply a new permutation. And for the network, I'm going to use a 3 hidden layer network with feed-forward layers and ReLU activations, trained using a stochastic gradient descent on the cross-entropy loss with a mini batch size of 30. And I'm going to use 4 settings for the network. The first one is a large network, relatively large network with 100 hidden units per layer. The second one is a small network with 10 hidden units per layer. Then a large network using layer normalization, and then a small network with layer normalization. I chose these 4 settings because I had 2 hypotheses about continual backprop. The first hypothesis was that continual backprop is less effective at maintaining plasticity in small networks. So here we're going to compare the performance of the large network against the small network. And if this hypothesis is true, we would expect continual backprop to maintain plasticity in the large network, but lose plasticity in the small network. The second hypothesis was that continual backpropagation is less effective when combined with layer normalization. This is just based on prior empirical observations. There hasn't been a systematic study about this. So, and layer normalization is such a popular technique that this is actually something that we would like to know. So this is why I chose these 4 different settings. So now I'm just going to straight up jump into the results, first in the large networks. So here's the plot for the large network. On the x-axis, I have the permutation number. And on the y-axis, I have the online accuracy. First, we have the base system without any modification on it. So we can see how it loses plasticity. It drops in performance over time. And just as another baseline, I have the base system, but trained using L2 regularization. It turns out that in this particular problem, using L2 regularization is a really good baseline. So beating that is kind of difficult. And now here's the performance of continual backprop. So again, this is as expected because it's a large network. I didn't expect continual backprop to lose plasticity, and it is very stable in its performance. So it seems that it's maintaining plasticity throughout the whole experiment. Now let's look at the performance of the large network with layer normalization. Again, here's the base system. And here's the base system using L2 regularization. We can see that this time L2 does lose some amount of plasticity, but it still is performing better than the base system. And now let's look at the performance of continual backprop. So here we can see that at the beginning it was doing pretty well, but over time it does drop in performance for a little bit. It's doing better than L2 regularization, but we can still see that it's losing performance and therefore losing plasticity. Okay, so how about the small network? So it's the same plot as before, just with a different type of network. Here is the base system. The losses in plasticity is more severe, even though the scale doesn't really doesn't make it look like it. Here's L2 regularization, which again is doing really good, surprisingly good. And now here's continual backprop. So we can see here how there's initial lose some amount of performance over time, and then it stays stable. So there is some amount of loss of plasticity, but it still maintains some performance over time. And now let's look at the same network using layer norm. Again, here's the base system and the baseline using L2 regularization. And now here's continual backpropagation. Again, we see a jump in performance and then a steady decrease in performance, implying that it's losing plasticity. So let's summarize all of these results in a table. Continual backpropagation maintains plasticity in large networks, but on the other 3 cases, it didn't maintain plasticity. It lost some amount of performance. So I would say for hypothesis 1, which was less effective in small networks, I would say this suggests that this is true. And for hypothesis 2, where I mentioned that maybe continual backprop was less effective with layer normalization, I would also say that this suggests that it's true. At least there's evidence to believe that. All right, so let's see if selective wave reinitialization can overcome these shortfalls of continual backprop. Okay, so is the algorithm. We have 2 layers, layer A and layer B. I really don't care which layers are these. The only thing that I care is that they are connected by these weights between each other. The algorithm, the first step is also the same as in continual backprop. We measure the utility of weights given some utility function. Then we select a number of these weights that have the lowest utility. And then we reinitialize the weights according to some reinitialization function. And that's the whole algorithm. You just do this on each of the different weight matrices in your network. So there are going to be 4 different choices this time. First is the reinitialization frequency, how often to reinitialize weights. Second is the reinitialization proportion, which is how many weights to reinitialize on each reinitialization step. Then the utility function and the reinitialization function. So the first 2 are just values that you choose for the algorithm. For the other 2, there's a little bit more nuance on how to select them. So I'm going to go through the utility functions and reinitialization functions that I used. For utility functions, I'm just going to borrow utility functions from the pruning literature. So in neural network pruning, usually people look at different measures to rank weights in order to choose the ones that are least useful for the network and then get rid of them, some computation or to save some memory. So this is a topic that is really heavily studied there. And two particular utility functions that have been demonstrated to be very useful there are weight magnitude utility, which is a function that simply takes the weight and returns its absolute value, and gradient magnitude utility, also known as saliency or gradient flow. This utility function actually has been rediscovered several times in the neural network pruning literature, but I'm just going to call it gradient magnitude utility. So for gradient magnitude, the utility of a weight is just defined as the weight, the absolute value of the weight, times the derivative of the loss with respect to that weight. So this GW term is simply the derivative of the loss function, given some input x and some label y with respect to w. All right, and now for reinitialization functions, one that I'm going to test is the obvious one. Rich? So this would be the expectation over all the inputs and labels pairs, but often we don't have that available to us. So we could either sample it, like we can take an average of, for example, over a mini batch, or we can keep a trace of the instantaneous gradient. Yes. All right. Right. No, I don't worry about that fact. I just keep using this all over again. Yeah. Okay, how about reinitialization functions? So the first is the obvious one used at the beginning. So at initialization, we said we sample weights according to some distribution. In this example, a normal distribution. A normal distribution with parameter mu I and I, which are just the mean and standard deviation of the initial distribution. So at reinitialization, we just use this same distribution again. We just select new weights, sample new weights from this same distribution. The second reinitialization function that I'm going to use is reinitialization to the mean of the initial distribution. So at initialization, everything is going to be the same as before. But now at reinitialization, I'm going to set new weights to the mean of this distribution. So there's no sampling here and there's no noise. This mean is usually, for most initialization functions, is usually 0. So what this means is that this first reinitialization function injects some randomness into the network, but also perturbs the weights in the network. This randomness might be useful because several prior works have shown that injecting randomness can help maintain plasticity. But perturbing the weights might actually be detrimental to the prediction of the network. On the other hand, this other initialization doesn't inject any randomness, but also doesn't perturb the weights all that much, because most of the time the weights that are being reinitialized are already very close to 0. So there's a contrast between these two, injecting randomness, but also perturbing the predictions of the network, or not injecting randomness and trying not to change the predictions of the networks all that much. So I'm going to try these two reinitialization functions combined to all the other two utility functions that I mentioned before. Any questions about this? Rich? Actually perturbing the waves to be randomly, at least in the first case. Mm-hmm. Okay. Your performance better. Using the performance, you reinitialize and then you train and test the end, or you're using an online performance measure that makes a change, so that's getting influenced by performance right away. Yeah, I'm using an online performance measure, so this could certainly hurt performance immediately after reinitializing. So that's also something that I want to keep in mind. like whether it hurts a lot of performance by quite a bit. Yeah. Sorry, what? Yeah, so I'm reinitializing both weights and bias. So in the bias case, these two are actually the same because we don't use a distribution to initialize bias. They're usually initialized to 0. Yeah. It might, but I'm not really worrying about catastrophic forgetting right now. I'm looking at loss of plasticity. So there are methods that definitely look to address both problems at the same time, but this method only worries about loss of plasticity. To address catastrophic forgetting, we will have to add something else to it. Russ? They're not, because the weights that are reinitialized are not exactly 0. They are very close to 0. So you just set them to 0 all over again. Like just make them 0. Yeah. You're right. It's counterintuitive, but it's another thing that I just tested, and we'll see the results. Okay, so let's look at the results of this algorithm with all those different settings. First in the large network, in the permuted MNIST problem. So this is the same plot as before. These lines you're already familiar with. I'm first going to show you the results for selective weight reinitialization with weight magnitude utility. They are these two lines. They are very funky looking, and I know it's not very encouraging because it looks like performance is going all over the place. And that's because when tuning hyperparameters, the best of parameters was to replace weights, reinitialize weights every 4,000 steps, and reinitialize 80% of them. So these drops that you see here are because we are basically almost reinitializing the whole network. Not very encouraging, I know. And most importantly, it's also not maintaining plasticity. So not so far, not looking good for this algorithm. Okay, let's look at the performance in layer norm. With the large network with layer norm. Again, weight magnitude utility. And we get a similar behavior, very thick lines going up and down very crazily, which is very undesirable, I know. And most importantly, again, it's not really maintaining plasticity. Maybe at the end it's kind of stable, but still not maintaining plasticity. So again, not very encouraging, but maybe let's look at the other utility function. So let's go back to this plot and let's look at grading utility. So now it doesn't look as bad. We can see that these two are different reinitialization functions. We can see that reinitializing with the initial distribution actually maintains plasticity, whereas reinitializing to the mean, it improves performance at the beginning, but it loses plasticity over time. Now let's look at the large network with layer normalization. Here are the results. Again, reinitializing weights with the initial distribution does maintain plasticity. The performance is not as crazy looking as the last one. And then reinitializing to the mean also seems to be more stable. It's not steadily decreasing, but it's also losing some performance from compared to the beginning. So there's some hope because at least we managed to maintain plasticity in some cases. Rich? Yes. Yeah. Yes. So my algorithm does have 2 hyperparameters instead of 1 compared to continual backprop. So you're jumping ahead, but because I was going to say that those could be combined, and that's something that I'm looking into next. But you're right; they could just be 1 hyperparameter, and that way we wouldn't have to tune 2 of them. So you're right; they could definitely be combined, and just do the same every single step. Okay, so now let's look at the performance in the small network. Again, this is the lines that you already know and love. And here's the performance with weight utility. Again, not really doing much compared to the base system. And now here's the performance with gradient utility. Just as before, reinitializing weights with the initial distribution seems to maintain plasticity, whereas reinitializing weights to the mean seems to do well at the beginning, but then drop in performance over time. Now for the small network with layer norm, here are the lines. This is the weight utility version, and here is the gradient utility version. So we can see now that both of them are actually doing pretty well. One of them is actually very close to the L2 regularization baseline. And this time, surprisingly, reinitialization to the mean managed to outperform reinitialization with the initial distribution, which was very surprising to me because, like as Ross pointed out, you're just setting the weights to 0 and then just keep learning after that. Okay, so in summary for this section, here are the two different types of utility functions and the two different types of reinitialization functions. For the large network, only gradient utility with reinitialization with initial distribution managed to maintain plasticity. Same for the small network and the large network with layer norm. But for the small network with layer norm, both of them maintain plasticity. And reinitialization to the mean actually had better performance, so I'm just gonna give it a second check mark. All right, but now the real question, the one thing that we really want to how do these two different algorithms or these two different ideas compare to each other? Is it better to reinitialize features or is it better to reinitialize weights? So let's look at the performance of both continual backprop and selective weight reinitialization. First, in the permuted MNIST problem with large networks. So here's the plot from continual backprop that I showed you before. And I'm just gonna add here the performance of the gradient utility version of selective weight reinitialization, which is here. We can see, again, this one lost plasticity, but the one that uses reinitialization with initial distribution did basically the same as continual backprop. There is a little bit more variance in the performance, but on average, it's about the same. And now for the large network with layer normalization, this is the plot that we had before. When we add the other two lines, we can see that selective weight reinitialization with initial distribution is actually maintaining plasticity. Now for small networks, here's the previous plot, and here are the other two lines. Again, selective weight reinitialization with the initial distribution is maintaining plasticity. And if we add layer norm, we get the same thing. Both of them are actually maintaining plasticity, whereas continual backprop loses plasticity in both of these cases. So again, in summary, continual backprop and selective weight reinitialization both maintain plasticity in large networks. In small networks, only selective weight reinitialization maintains plasticity, as well as in the large network with layer norm and the small network with layer norm. So this seems encouraging. Okay, this seems encouraging, but so far it's a very small problem. It's like MNIST. It's like a toy problem that nobody really cares about in industry. It's a very simple architecture. Like, who knows if like real architectures will actually lose plasticity the way that we observe here. So maybe all of these results are just gonna be completely pointless when we move on to modern architectures. So the next step is to evaluate these algorithms in a bigger problem with more advanced architectures. But before I move on to that, I want to say something about the difficulty of reinitializing features in any arbitrary architecture. When I presented to you the continual backprop algorithm, I'll show you this diagram where it's just a hidden layer. This diagram kind of abstracts away the type of layers that we could encounter. For example, this could be a hidden layer. It could be a feed-forward layer. It could be a convolutional layer. It could be a patch norm, layer norm. It could be an attention layer, an LSTM. It could be many different types of layers. And the problem with this is that different layers have different notions of what it means to be a feature. And that's gonna determine how to compute the utility. So that means like for each of them, we have to go back into the drawing board and figure out what does it mean to be a feature and figure out how to compute the utility for that feature. So far, we've been able to do it for feed-forward layers, convolutional layers, and batch norm. We know how to do it with layer norm, but as I've shown you, sometimes that doesn't maintain plasticity. And for the rest, we still haven't figured it out. So we will have to go in, dig deep, write down all the equations, and figure out how to compute the utility for each of these different layers. And the problem gets even more complicated in big architectures because we have a combination of all of these layers. For example, we could have a convolutional layer connected to an attention layer, then a feed-forward layer, and then a layer normalization layer. And for each of these different ones, we will have to figure out how to compute the utility for each of their features. The advantage of selective weight reinitialization is that we don't even have to do that. I don't even care what type of layer it is. I just care that it has weights and biases, and I can apply selective weight reinitialization on it. So transferring the algorithm from one architecture to another one is really easy. But that doesn't mean that it's actually going to be successful at maintaining plasticity. Maybe to apply, but it's terrible at maintaining plasticity, and we're still better off using continual backprop. So let's see. Let's have some comparisons in modern architectures. For this particular part of the talk, I'm going to use the incremental CIFAR 100 problem. So the CIFAR 100 dataset is a dataset of images of size 32 by 32 by 3. Networks are trained to match images to 100 possible labels. There are 500 images for training and 100 images for testing per class. The incremental CIFAR 100 problem is simply a sequence of classification tasks with increasing number of classes. Specifically, we're going to start different classes. We're going to train a network to distinguish between all of them for some number of epochs. Then we're going to add 5 more classes, and we're going to keep training the network on these 10 different classes. And we're going to continue on until we have a data set with 100 classes. And we're just going to train the network incrementally and see if it loses performance over time. Now, as described here, we could run into 2 different problems that affect performance that have nothing to do with loss of plasticity. The first one is forgetting. If the network is never trained on these 5 initial classes that we saw at the beginning, it might have forgotten about them by this time. But to prevent that, we are just going to train the network constantly on all the previous classes observed so far. So that way, there's no risk of forgetting all the information. But this can lead to another problem because the network is constantly being trained on all classes. And maybe it might overfit to all classes and not be able to learn from new ones. So we also need to find a way to prevent overfitting. And to do that, I'm going to use image transformation, which has been shown to be very effective at preventing overfitting. And I'm also going to use early stopping. So I'm going to train the network until I see that the validation accuracy starts decreasing. I could give you more details about this later on, but for the moment, just accept that this helps prevent the problem of overfitting. For the measure of performance, I'm going to use the highest test accuracy on each set of classes. And to actually evaluate if a network is losing plasticity, I'm going to take the difference in performance between a network trained incrementally and a network trained from scratch on the same set of classes. All right, so now let me tell you a little bit about the architectures. So I'm going to test 2 different types of architectures. The first one is a ResNet 18. This architecture, the basic unit is a residual block. And now I'm going to speed run through this explanation. A residual block basically takes an input that goes through a convolutional layer, a batch normalization layer, and then a ReLU activation. And then it goes through another set of those. There's an input, there's a skip connection from the input to right before the second activation, and that gives us the output. The ResNet 18 architecture is simply a stack of these blocks. So an input image goes through a convolutional layer, a batch norm, a ReLU activation, and then a stack of residual blocks. Then it goes through an average pooling layer and a feed-forward layer. And finally, we get the output. The continual backprop is used between every pair of convolutional layers in this architecture. And this architecture has about 11 million parameters. Now, for vision transformer, the basic unit is an encoder block, which takes an input, goes through a layer normalization layer, a self-attention layer, a dropout, goes through another layer normalization. There's a skip connection from here to here. And then we have a stack of feed-forward layers with a yellow activation in between. And finally, we get our output, and there's a skip connection from here to here. Continual backprop is used between the feed-forward layers, so right here. And a vision transformer is just a stack of these blocks. So an input image goes through a convolutional layer, dropout, several encoded blocks, layer normalization, feed-forward layer, and finally an output. Now, if that seemed overwhelming to you, it's because it is intended. I didn't really want you to understand exactly how these architectures work. I wanted you to get a sense of how complicated they are. Because in their complexity, there's also the problem of how to apply continual backprop to each of those different layers that I show you. So again, you don't need to understand the architectures. You just need to understand that they are very complicated. Oh yeah, this network has 14 million parameters. And the good thing is selective reinitialization doesn't even care about what architecture we have. We just apply it on every weight and bias term in the network. Okay, so now let's look at the results. So here is the plot with the number of classes in the x-axis and the test accuracy on the y-axis. This is the base system trained from scratch. So it's initialized at the start of each task. And here is the base system trained incrementally, which is initialized only at the very beginning and then just constantly being trained after that. We can see here that at the end, the base system is doing worse than the base system trained from scratch, which shows some loss of plasticity. But what we really care to show plasticity is not each of these lines, but the difference between these two lines. So I'm going to plot the difference. I'm going to plot the gray line minus the blue line minus the gray line in the next plot. So this is going to be the accuracy relative to the network trained from scratch. Here is the plot for the base system. So we can see that at the beginning, we see an increase in performance compared to the network trained from scratch, but then we see a steady drop in performance. And by the end, it has lost more than 4% accuracy compared to the network trained from scratch. This is what really shows that the network is losing plasticity. Now let's see how we can maintain plasticity in this particular problem. One simple baseline in this case is to just reset the output layer. So that's another form of selective reinitialization that I really haven't talked about in this talk so far. So let's try it out. And this is the performance that you would observe. So it is helping a little bit, but it's definitely not getting rid of the problem. It is maintaining some accuracy compared to the network trained from scratch, but we still see a drop in performance. Next, let's see what continual backprop does. So continual backpropagation does completely get rid of the problem of loss of plasticity. It managed to, at the end, perform essentially the same as the network trained from scratch. And now the real question is whether selective reinitialization is also going to maintain plasticity. And here's the line. So it is not performing as well as continual backprop, but by the end, it is still performing as well as the network trained from scratch. Perhaps there's a gap here, but it still stays fairly close to zero. And then at the end, it's still performing the same as continual backpropagation. So it's not a complete victory over continual backpropagation, but it does show that it maintains plasticity. All right, so now let's move to the vision transformer. Again, we have the same plot as before. Here is the system, the base system trained from scratch. And here's the base system trained incrementally. And now let's take the difference, the blue line minus the gray line, and it would look like this. So in this case, the effect is way more severe. At the beginning, we see a really big, a big improvement in performance, close to 4%. But then over time, the difference in performance goes all the way to minus 10%. So there's a very steep drop in performance in this case. Now, another type of selective reinitialization algorithm that I tested was reinitializing just the layer norm parameters at the start of each different task. So that means like at the start of the task, I just reinitialize the layer norm parameters, and then I train the network. If we do that, we actually see some gains in performance. It is still losing plasticity, but there's a big improvement from here to here. So that's great. Now let's try continual backpropagation. So we can see this time continual backprop wasn't effective at maintaining plasticity here, but I gotta admit, like, it's only being used in between those feed-forward layers in the encoder block. So it's not being applied everywhere on the network, but that's also because I don't know how to apply it in other places. And now let's look at selective wave reinitialization. So now we can see that selective wave reinitialization is doing way better this time, effectively maintaining plasticity all the way through. And here I would like to declare the win and just move on and say that you should always use selective wave reinitialization, but that's not true. Sorry. But that would be not giving continual backprop a good shot, because, and again, continual backprop is only being used in the feed-forward layers. So what I'm going to do is combine continual backpropagation with layer norm resetting and see how that performs. And if you do that, we actually get pretty good performance all over again. So it means that resetting the layer norm was also important for maintaining plasticity. And it's actually performing just the same as selective wave reinitialization. For me, it was a little bit discouraging, but at the same time, it shows that the effectiveness of selective reinitialization in general for maintaining plasticity. There's also a big difference between these two lines. This line, at least, has knowledge about when the tasks are changing, whereas selective wave reinitialization really doesn't care about when each task changes. It just continues doing the same thing over and over and over again. Sometimes that might be desirable because sometimes you don't really know when tasks are changing, and sometimes you don't care, and you just can look at when the task changes and then do something different each time. So that's it. In conclusion, first, let me revisit my main takeaway. So I told you that selectively reinitializing weights is more flexible and more effective at maintaining plasticity than selectively reinitializing features. And I feel that's too broad, given what I've shown you so far. So I'm going to revisit this takeaway. Instead, I'm going to say selective weight reinitialization can be easily applied to any arbitrary architecture, whereas continual backpropagation requires some additional considerations. That's what I meant with it's more flexible. It can be applied easily to any architecture. Additionally, selective weight reinitialization is more effective at maintaining plasticity than continual backpropagation in small networks and when using layer normalization. But both are still very effective ways for maintaining plasticity. So now this is something that I'm comfortable with as a takeaway. Okay, and now, Rich, I saw you. For those in Zoom, Rich is saying that I'm still overclaiming, even though I revisited my main takeaway. And I should instead say that in the two experiments that I presented, this is true. But if we move on to other data sets, or maybe reinforcement learning, or any other problem, we might not see the same pattern. And I agree. I just also thought that it was already very long, but that would be a more specific, more honest takeaway. Okay, so in conclusion, selective reinitialization is a good way for maintaining plasticity. Both continual backpropagation and selective wave reinitialization are effective at maintaining plasticity. Applying selective wave reinitialization is easy and more straightforward than continual backprop, but still both of them are pretty good at maintaining plasticity. And finally, I didn't touch on this very much, but modern architectures are not immune to loss of plasticity. Many times when we present our results in conferences, especially since plasticity is just recently gaining attention, people are like, oh yeah, well, you're testing this in very small networks. You're testing in very silly problems like MNIST, who cares about that? We've solved it like decades ago. But I've shown you that even modern architectures such as ResNet 18 and Vision transformers, which are still particularly small, but they are closer to what people use in practice, even those networks can show loss of plasticity. And now for future work, again, I'm looking at reducing the number of hyperparameters. Like Rich mentioned, we could combine the reinitialization frequency and reinitialization proportion into a single hyperparameter, like in continual backprop. And I'm also looking into trying other reinitialization functions. Like we saw that there was really no consensus on which reinitialization function was better. Sometimes reinitialization to the mean was more effective. Sometimes reinitialization with initial distribution was more effective. So it means that sometimes there's some amount of noise required for maintaining plasticity. And neither of these is particularly good at doing that. My idea is that maybe if you tune the standard deviation of the reinitialization distribution, maybe you might gain better performance, but that's something for future work. Other than that, thank you so much for staying with me. I want to say thank you to my collaborators, Shivansh, Parash, Chinfeng, Rupam, and Rich. Also, thank you for Rohan for the conversations about applying selective wave initialization to language models, which is something that I'm looking to do next. And thank you to Suyog, Anna, and Andy, and Aiden for helping me practice this talk. Thank you.